Advent of Code are a series of programming challenges that are published every year in December. There are 2 problems for every day leading up to Christmas, giving a total of 50. In the previous video, I did the first challenge of the first day, so now we're going to take a look at the second challenge on the first day, which is probably going to be a sequel to the first one. Funciton is an esoteric programming language that I invented, and I'm going to attempt these Advent of Code challenges in that language. Now, in the first challenge, we were given a file that looks like this, where you have 2 numbers separated by 3 spaces, and we were supposed to sort the left column and the right column independently, and then calculate the differences, the absolute differences, between every pair of numbers in the sorted lists, and then output the sum of all of those differences. And this is what the Funciton program looked like. We took the standard input, we split it at every occurrence of a new line, and then we used the map function twice with 2 different functions. So this here is the string consisting of 3 spaces, and then we're splitting the string in those places. But you can see that up here we're using the output that comes out of the left, whereas here we're using the output that comes down the bottom. Which means that this one here will obtain the first integer in each row, and this one here the second one. And then each of those we run through the sort function, which we wrote in the previous video, and then we zip up those 2 sorted lists so that every pair of integers now goes through this lambda expression, which will do the subtraction and then run the absolute value through that, and then we sum up all of the results and return the resulting integer as a string. Now, I haven't looked at the second part of the challenge yet, so I'm going in completely blind. Let's take a look at what it says. This time, you'll need to figure out exactly how often each number from the left list appears in the right list. Calculate a total similarity score by adding up each number in the left list after multiplying it by the number of times that number appears in the right list. Okay, here are the same example lists again. So for these example lists, here is the process of finding the similarity score. The first number in the left list is 3. It appears in the right list 3 times, indeed. So the similarity score increases by 9. The second number in the left list is a 4. It appears in the right list once, so the similarity score is just 4. The third number does not appear in the right list at all, so it's 0. So for these example lists, the similarity score at the end of this process is 31, which is the sum of each of these multiplications, right? 9 plus 4, yeah, indeed it is. Once again, consider your left and right lists. What is their similarity score? If I understand this correctly, we're no longer sorting the list, and we're no longer calculating the differences, but instead we're taking only the left list, and we're finding out how many times each number occurs in the right list. Alright, the 2 challenges look kind of different, but the one thing they still have in common is that we're still splitting each of the lines in the text file at the 3 spaces. So most of this code is still going to stay the same, but we're no longer going to sort the lists, so I'm going to remove this sort function here, and then I'm also going to remove everything below this point because we don't do that anymore. So this is still going to be the list of the numbers on the right-hand side, and this is the list of numbers on the left-hand side. So what I want to do is I want to multiply every number in the left-hand list, which is this one here, by some number that we obtain from here. So I'm actually going to run map on this again. Now I could incorporate this inside this lambda expression, but just due to the geometry, I think it's just more convenient right now to map over it a second time. Okay, so for every number on the left side, that number is going to come out of the lambda expression up here. So now we need to multiply it with something. Right, okay, so here's what we're going to do is we're going to take this list and we're going to filter it by this number and then count how many times that happens. But then, of course, we also need to multiply by that number. So I actually need to take a copy of this number. Okay, so we need to filter this. So let's just put a filter box here, a filter function call. So if this is the list, then the lambda expression will go on the bottom and the result will come out on the right. Hang on. Maybe I don't need to use filter. Maybe I have a function that will just count the number of matches based on a lambda expression. I found the function that I was thinking of. It's this one here. but I misremembered how it works. It turns out that it uses lists rather than lazy sequences. So I'm still going to use filter and count, because I think the reason that I don't have count matches for lazy sequence is precisely because you can just use filter and count. Okay, let's make some extra space here, and let's put a lambda expression box right underneath this. Okay, so this is the lambda, so this is the input, which is a number from this, and we want to check whether that is equal to this number here. Well, let's write the multiplication first. No, not multiplication, equals. We need, I'm getting ahead of myself. So we need an equal sign here. And then here we need to put in that. So looking at the filter, we're passing in a lambda expression. So this is lambda, and then counterclockwise order, this is the input, which we want to check against something. And then this is the output. So that's where the result of the equals comparison needs to go. And then this is once again the second output of the lambda expression, which doesn't matter. So I'm going to pass in 0. And now that we've filtered that list, this is where the filtered list comes out. So we now need to count the number of elements in it. Okay, so now we need to multiply this number with this number. So I'm going to switch this around. So this is where the condition goes into the equal sign, and then this one here is going to need to be multiplied. So let's put a multiplication box here. And now the result of that needs to go into the output of this lambda expression. So let's think, this is where the lambda is, this is the input, so we need it to go in here. And then this is the output that doesn't matter. So I'm still going to put 0 in there. And then we can place this line all the way around, and that should be the lambda expression for this map. So after this, we should have the results of all of those multiplications. So I think we want to sum that up. So I'm going to go back to the solution to the first problem, because we have the sum and the integer to string function right here. I can just copy that and place it right here. And then let's try this. Now I'm first going to try this on something simple. If I do 1, 1, what do I expect? I expect 1 times 1, which is 1. So let's see if that works. If I now run the second part and I pass in the test, no, not that. I meant the txt file. Okay, I do get a 1. Let's try the example that they gave here. And we're supposed to get 31. Let's see if we get 31. We do in fact get 31. Wow. So once again, first try. That means I can now run it on the complete puzzle input, which, by the way, I called it 1a.txt earlier, but I realized that this is going to be the same for both. So I'm just going to call it 1.txt from now on. And once again, this is going to take a while because Funciton is an esoteric programming language. And the reason it's so slow is because everything, including addition, multiplication, all the string handling and everything, is itself implemented in Funciton on the basis of some very simple foundational built-ins. I made an entire video series on this, link in the description if you're interested in learning how Funciton works. Now, of course, there's always the possibility that there is a bug in the program due to which it might actually run forever. So I'm just gonna have to be patient, and if it doesn't finish in an hour, then I will cancel it and look for bugs. 1 hour later. Well, I don't know how long this took. I went away to watch an episode of Star Trek while I was waiting for this, but it has come back with an answer. So let's put that in our clipboard and let's put it here on the website. Submit that as our answer. And it turns out it is, in fact, the right answer. So we're done for today, right? 10 hours later. Well, good morning, everybody. And now that I've slept over it, I've decided that that wasn't good enough, what I've done. I've actually run the solution again just to see how long it actually took. It turns out it took 28 minutes and 13 seconds, which is quite a lot. Even the first one, okay, this one's not quite as bad, but 6.7 seconds. Let's see if we can improve upon that. You see, while I was in bed and in the shower, I actually came up with multiple ways that I could optimize this solution. And I think you deserve to know that Funciton can do better. Now, one way that the sort function that we wrote is kind of suboptimal is that it uses two separate invocations of the filter function, one here and one here, to sort through the same list. Once to find all the elements that are less than the head, and then the ones that are greater than or equal to the head. So I think we can optimize that by going through the list only once and sorting it into 2 lists in one fell swoop. So if you want to think about how you can do this, pause the video here, maybe put your guess in the comments box, and I'm going to make space here for a new implementation, and if it's successful, then I'm just going to erase the first one. So here's what I'm going to do, is I'm going to use a helper function. And this helper function is going to receive the pivot, which is the element that we're comparing against, and the sequence, which we want to sort into the less than and greater equal to pieces. So let's start with the declaration this time. And I'm going to call this function the same as I did the sort function, but with an extra p for private. And then I'm also going to actually make it private, which I do by adding this little tag in the top left corner of the declaration box. Now the first argument we're going to process is the sequence, and the second one is the pivot. Now obviously if the input sequence is empty, then we want the results to be empty sequences. Now the first thing that we're going to need to do with the sequence is we're going to need to split it into head and tail, because we've now checked if it's empty, so if it's not empty then we can do that. Remember that lazy sequences are lambda expressions, so I'm going to call the lambda expression here. So this is the lambda expression, which means this is the input, and of course lazy sequences don't care about their input, so I'm just going to put a 0 there. And then this is the first output, and this is the second output, the first output being the head, and the second output being the tail. Now we're going to need to compare the head against the pivot. I think I'm going to start by putting a wire crossing function here so that the tail can come through. And now I need to check whether the pivot is less than the head. Okay, now let's think about what our first input one... Oh, I just realized that the directions of the inputs, since we're gonna have 2 outputs, which are of course at 90-degree angles from one another, we need the inputs to also be at 90-degree angles from one another. Okay, so what do we need to do in this case? Well, we want all of the elements that are in fact less than the pivot. So all of the elements where this gave us true. So if it did give us true, then we need to apply the head to the recursive call. And otherwise, we just return the recursive call. So we're going to need a question mark right here. And then this is where the condition goes in, the pivot less than head condition. And then, of course, I'm going to take a copy of that condition because that's going to go in the other question mark as well, which I haven't dealt with yet. So if that is true, then we need to create another lambda expression which represents a lazy sequence. So if this is the lambda expression, then this is the input, which means that that needs to... Yeah, that can just be 0. Maybe I didn't need the wire crossing function, but whatever, I've done it now. So I'm just going to put the 0 on the other side of the wire crossing function. And this would be the first output, which would be the head. So I guess we're going to put head there, but we're still going to need a copy of the head for the other case. So I'm going to make some room here for the head to be able to push through. Okay, and then this needs to be the tail, which is the result of the recursive call. But then the else condition on the question mark is also going to be the result of the recursive call. We can combine those into one. And what's the recursive call going to look like? Well, if this is the first output of the recursive call, and this is the second one, which we're going to need over here. So I'm quickly considering whether it might be wise to actually move this over here, but I guess I can still do that later. So what needs to go into the recursive call? Well, the first argument is, of course, the sequence, which in this case is going to be the tail. So that needs to go here. And then the other one is the pivot, which is this one here. So we're going to need to cross some more wires. And then this here needs to be the pivot. Now I'm going to connect up the tails later. I need to worry first about this bit here, which needs to connect with something over here. Now we haven't written much of the code for this yet. So actually I'm considering now moving this part inside of this empty space. So I would have to expand this in order for it to fit. But let's write it first so that we can tell how big it's going to be. Okay, so here's our second output. This is the sequence. Now if the sequence is non-empty, then we need to check if the pivot condition is true, right? Okay, so this is the condition, which is what comes out of here. So we need to take a copy of that. Hang on. So if I were to put this whole thing over here, then I could have this go the other way and then punch through this. So that would still work. In the case where this is true, we want to create another one of those lambda expressions because we want to return a sequence with the... No, wait, that's not true. This time it's the other way around. Right here it's the true case that wanted the lambda expression, but this time it's the false case. So let's put the lambda expression here, and we'll immediately see that this 0 box kind of interferes with it, because if this is the lambda expression, then this is going to be the input, so we want a 0 there, and then this is output 1, which is the head, and this is output 2, which is going to be the tail. I think what I'm going to do is I'm going to put that lambda expression box here. So now, if I attach this, so we said that in the yes case, so this would have to be the recursive call, which is this thing here, right? That would need to go here. So I'm going to label that as this is where R comes out. So if this is the lambda expression and this is its input, so this wants to have a 0 on it, and then this is the head, and then this is the result of the recursive call, and this is R. It was quite a lot more convenient how the recursive calls lined up over here, but now they line up kind of badly. There's nothing I can do about that, so I'm just going to expand this. Okay, so now if I imagine putting all of that inside of this space here, I think that actually works. So let's do that. Okay, so we want the sequence here, so let's move this over. Okay, so this is now the sequence, so we can now comfortably just connect this up. Oh, there is another thing here that needs the sequence as well. I mustn't lose sight of this. Okay, so now I can connect these up. Now the condition is this bit here. So we need another wire crossing function that punches through here. So far so good. The next thing we need is R. Now R is here. Oh dear. Oh dear, this is gonna require a lot of wire crossing, doesn't it? Oh, wait a second. Oh, there is a wire crossing function here, so I can actually just take this R and put it in here. Okay, now this is, hang on, so this is where R goes in, and R is the, that's right, so this is the input to the lambda expression, which doesn't care about its input, so we're gonna put a 0 there. I think that this is actually where the tail comes out, isn't it? Because this is the lambda expression that we call on the sequence, and this is the input, this is the first output, which is the head, and we're comparing that against the pivot, so this is where the tail comes out. So I should have put an arrow there. Okay, so that needs to connect up with this one down here. Okay, now I can join up that sequence. Right, these are not... Yes, actually, this is where the head comes out. Again, I forgot to mark that with an arrow, because this is the result of that lambda expression. So let's see if I can save on wire crossing, because if I were to go around here, I would have to put a wire crossing here and then 2 more to punch through these wires. But I think that if I branch it off here instead, then not only can I remove this one here, but also I can fit it in here with only 1 wire crossing. So this is what I'm going to do. And that requires me to move all of this code up. Okay, but now there is only 2 lines of space here. So maybe I'm going to move it up 1 more. Okay, so now we can punch through this wire. Okay, just for aesthetic purposes. Here's one thing that I almost forgot. Remember that we're using the question mark to check if the sequence is empty, but the second question mark actually checks against the output of the less than function, which we already know is either 0 or -1. So I can actually use the interrobang function here, which is optimized for that case. Okay, so that's the helper function. We now have a helper function that can split a sequence into 2 sequences. So now let's write the main function for sorting. We want to check if it's empty or not. Okay. So if it's not empty, then we need to take off the first element from the sequence. So we need a lambda expression like this one here. No, wrong. This is a lambda expression. What we need is we need to call the lambda expression. This is the lambda expression, and it doesn't care about its input, so we're going to put a 0 in there. I think I may have made a mistake here because I noticed that there is a 0. Right. Okay, we need to silence the input, not pass in 0. And we need to do the same thing here. We do indeed not need this wire crossing function. You know what just occurred to me? Look at these boxes here. I can theoretically move them all the way to the left, like here. And now we can save one line of code. Okay, back to the sort function. Okay, so we've got a lambda expression. So this is the sequence, which is a lambda expression. So this is going to be the input, and it doesn't care about its input. So we're going to pass in a 0. And then the first output is going to be the head, which becomes our pivot. So I'm going to call that the pivot. And then this is the tail, which is the sequence that we're going to be passing into the helper function, isn't it? So let's call the helper function, which is this one here, directly on the tail. And then I'm going to put the pivot right in here. We are still going to need the pivot because remember that we want the sequence of elements that are less than the pivot, then the pivot, and then the sequence of elements that are greater than or equal to the pivot. What I actually want at the end is a concatenation. So actually let's put the concatenation function here first. So this is going to be the first sequence, which is literally just the sequence that comes out of the first output here, which is this one, unfortunately. It would have been nice if I could just connect this, but no, it's actually this one. And then after that, we want a sequence that starts with the pivot. So let's actually put a lambda expression there right now. So this is the lambda expression. This is the input to the lambda expression, which we don't care about. So I'm just going to silence it. Then this is the first output, which needs to be the pivot. And then this is, right, okay, so this is going to be the other sequence. Okay, so we can actually do this by just punching through this wire only. Well, it looks like I can just move this down. So that is the lambda expression we're calling, then this is the input and this is an output. So that means that is where the pivot comes out, and we want the pivot to go in here. And then we need another copy of it. So I need to put the splitter here. Well, I don't need to, but this is one place where I can put it, and it comes out of here. Right, so this is wrong. Okay, and then that needs to go in here, so let's just connect that up. So this looks like we're done, but I actually forgot that each of the individual sequences need to be sorted again, so we need to insert some recursive calls. Whoops. So let's see, so this is the output. Right, yeah, we literally just need to put the recursive call on each of the two outputs of this. Okay, now let's move this slightly down so that it is more centrally aligned with this. And now we need to test this, but we now have two functions of the same name. So I'm going to rename this one. I'm going to rename it to old. Now I still have the test program from yesterday that we used to test the sort function. So let's see if the sort function that we just wrote actually works. So I'm going to try this with numbers that are already sorted. And it should just give me 1, 2, 3. And it sorts them backwards. Well, that's interesting. So let's see what happens if I just put some random numbers together. Indeed, I always get them in reverse order. Now, fortunately, that is very easy to fix because all we need to do is just change the less than to a greater than. Now, let me quickly try and figure out why this is the case. So the first input here is the sequence, and this is the pivot. So we're taking pivot greater than number. Indeed, we wanted the condition number less than pivot. So that's the same as pivot greater than number. And indeed, there we go. Okay, second try. All right, now that we've written a new sort function, let's test the solution to the first problem again, which uses the sort function twice. And let me just run that with a measurement. Okay, there we go. It's about 8 seconds. Now in the previous timing it was 6.7 seconds, but that was when the video recording software was not running. I'm recording now, so that slows it down. So we need to use the old function as well in order to compare the two. So I'm going to change the old sort function so that all of its recursive calls actually call that. And then I'm going to change the solution to the first problem to use that same one. And then we can measure that with the video software running. There we go, it's 8.3 seconds, so it's actually slightly slower. So we have actually managed to optimize it just a little bit. So I guess we can safely get rid of the old sort function now, and we can put that comment right here to label the new sort function. Okay, now let's get to the second part of the problem, where I think I can do a substantially more significant performance improvement than what you've just seen. Because I think the main thing that makes this solution so incredibly slow is that as it goes through all the elements in the left list, it's going to go through the entire right list for every one of them. The input file has 1000 lines, which means that for every one of those 1000 lines, it's going to go through all 1000 lines on the right-hand side, which means it's doing a million things, literally. 1 million, 1000 times 1000. So, I think I can improve on that, and here's how I'm going to do it. Again, pause the video if you want to think about it and see if you come up with the same solution that I do. So the first thing that I'm going to do is I'm going to split the entire input into two sequences representing the left column and the right column, and I'm going to use the exact same strategy as I just did with the sort function. Our current solution does it twice, and each time it discards one of them. So we can do better by just calling the string split function only once per line, and actually using both of its outputs. And I think I want to sort them both, because that makes the following algorithm possible. So imagine you have these two lists and they are both sorted. What we can now do is we can look at the first element of both of those sequences. If they are different, then we can always discard the smaller one, because the other list is not going to contain that smaller element because it's sorted. So we can keep discarding the smaller element until we run into a case where the two elements are equal. And only then do we actually need to do some calculation. And the calculation that we need to do is to figure out how many times that element occurs at the start of the left list and how many times it occurs at the start of the right list. And for both of those, we only need to look at the start of the list, right? We can stop as soon as we find any number that is not the same. And then once we know how many occurrences of that element occur, well, we can just take the number of occurrences on the left times the number of occurrences on the right times the number itself. So I think that having to sort the lists, which we're not currently doing, is worth the trade-off, because once we've sorted them, we only need to go through both lists once instead of 1000 times. I'm going to start a new file. I just want to start with this, where I'm splitting the input at the new lines, and now I have a list of lines of text. And I want to use a function very similar to the helper function that we wrote for the sorting function. But the fact that we need a map instead of a filter makes it sufficiently different. So I'm going to rewrite this from scratch. Once again, we need to start with 2 question marks, because we need to check if the input sequence is empty. I'm going to start with the first question mark first, the one that will return the left column. So if that sequence is empty, then we need a 0. Else, we will always need to return a lambda expression in the case where the input sequence is not empty. So I'm just going to put a lambda expression box right here. So this is where the lambda expression goes. This is where the input comes out, but of course this is a sequence, so it doesn't care about the input. And then the head of this is of course the result of the mapping. And the result of the mapping in our case is the string split function. And if this is the first output, then this is going to be the second output, which means that this is where the line goes. So I'm going to call it the line of text, okay? And this is where the separator goes. Now the separator consists of 3 spaces, which is of course this big number right here. Now the tail for this lambda expression is going to be a recursive call. Okay, so this needs to receive the first output from the recursive call. I'm just going to call that R1. So now let's do the other question mark thing. Now, if the sequence is not empty, then once again, we need a lambda expression. And then this is the head. So that is where we put the other output from the string split. Okay, and then this one is going to contain the other output of the recursive call. The 2 recursive outputs are going to come out in counterclockwise order. So I think I'm going to put a wire crossing function right here so that the R1 can go through there. And then I'm going to put the recursive call here. So what am I going to call this function? Well, since this is the first day of Advent of Code, I'm just going to call it 1 in a circle. So that is the first output, that is the second output, which means that this needs to be the tail of the sequence. And as I think about what would the other one be, we really only need one input, don't we? We have a single sequence, which is the sequence of lines of text, and we want to split every element into two, so we end up with two sequences out. So we only have one input, which means that I'm not going to make it a 90-degree angle like this. Instead, I'm going to move this over to here, and then this is where the tail goes in. And the line of text, of course, is the head, because it's the first element of the sequence. So once again, this is quite convenient, actually. So we just call the lambda expression right here, and the head or line will come out the bottom, and then the tail will come out the right. Awesome. So this is a lambda expression, which means that this is where the sequence goes in, and this is the input that it doesn't care about. We still need to connect these. Okay, so the sequence goes in here, and here, and here. And then I can put the declaration box here. I'm just going to plonk it right here. Okay, and we're going to use the one in a circle, and we're going to declare it private. Okay, so that's the helper function. Now let's go back to the main program. We want to pass our sequence right into that helper function, and it's going to give us two sequences, and then we want to sort both of those sequences. And now we have both of those sorted lists. So this is our first helper function taken care of. So the next thing is that algorithm that I described. So we're going to need a helper function for that as well. So to focus on the second helper function, I'm going to make more space in the bottom of the file. We have two sequences. As soon as one of the sequences is empty, we can just immediately stop. So once we get to here, we know that both of the sequences are not empty, which means that we can obtain the head of both of them. The next condition that we want to check is whether head 1 is less than head 2. If h1 is in fact less than h2, then we want the result of a recursive call. But then if it isn't, we're going to have another condition. So I think I'm going to flip this condition around so that I can put the recursive call over here on the left and keep stacking these conditions on top of one another. So if h1 is less than h2, then we're on the else branch here. So we want a recursive call here. So at this point, I'm going to need to settle on a name for the function. And since we already have a 1 in a circle for the first one, why don't we do a 1 in a double circle for this one? This function is going to take two arguments and have only one result. h1 is the one that was smaller. So h1 is the one that we need to remove. So here we want to put the tail of the first sequence, and here we want to put the full second sequence. Over here we're going to have something very similar, but now if I put the thing on the else branch here, it's going to collide with this. So this time I'm actually going to put it like this. And then the recursive call is going to go on top. And the first argument this time is going to be sequence 1, and the other one is going to be the tail of sequence 2. That means that this is basically the final else branch. So this is where h1 is equal to h2. So at this point, we want to calculate how many times that number occurs at the start of each of those sequences. And it smells like I'm going to do another helper function for that. So let's defer that until later. So this is where we're going to count the head elements. Well, let's write the conditions first, the greater or equal to and the less than. I think I'm going to make it so that h1 is going to go here. So I'm going to switch this over, and we can now see that these are, of course, booleans. So we can actually use the optimized interrobang function. Head 1 is the result of a lambda expression call. And this is the input to the lambda, which we don't care about. Okay, so now I need to connect up the tail 1 with that tail 1. It just occurred to me that we probably want tail 1 and tail 2 for the count thing as well. So in order to not lose track of this, I'm going to put tail 2 here. Oh, there's another tail. Oops, sorry, this is tail 1. Now let's do tail 2 and head 2. And we can obtain head 2 with a lambda expression like this one here. So if the head 2 comes out here, then the tail 2 will come out here, which means that this is the lambda expression, which is the sequence, so that's sequence 2. And then this is the input that we don't care about. Make it look a little bit more symmetric. Now this is tail 2, which only needs to connect with this and potentially the C. So why don't I do the same thing as I did earlier? And as I do this, it occurs to me that I can actually stack this on top of this line. Now, what do we need in order to do this calculation? We need to count how many times head 1 or head 2, which we now know to be equal, occurs at the start of tail 2, and then we need to add one more because we've already removed one. That's why it's called the tail. Now, we know that head 1 is over here, so this is going to be a little hard to extract, but this here is head 2, and I think we can get that out of here, which I'm now just going to call the head, because we know that the two heads are equal at this point. So over here, we want to call a helper function that will take the tail 2 as its first argument, and the number as a second argument. Does it need to return one or two things? I think it needs to return both the count that it receives and the rest of the sequence. So if the sequence starts with, let's say, 3 copies of the number 47 or whatever, we need to have the number 3, but we also need the rest of the sequence with the 47s removed. So this is going to be a 2 input, 2 output function, and we're going to need 2 of them because we run it both on tail 2 and on tail 1. Let's put a function call right here, and let's also give it a name. So I'm going to call it this, circled -1. Well, negative as in negative space, not negative number. So it takes the tail, and then it needs to take the head, which, by the way, again, I forgot to mark that this is where the head comes out. And then this is going to be the amount, so I'm going to say number here, and then this is the rest of the sequence. So that's going to be the tail, the tail of the tail. This part here needs to do something very similar, doesn't it? It's also going to need access to h. Right, so if the tail 1 is going to come in on the bottom, then the head needs to come in on the right. Gosh, these boxes are so close to one another, they're all going to interfere with one another, aren't they? So this is where the head needs to go in. It just occurred to me that we're using this wire crossing just to cancel out this wire crossing. Right, the head actually comes out the bottom of here. So I could actually have it come out of there immediately. Bingo. And this is great because now we have space for a another wire cross, because we're going to need to escape the sequence 1 at some point, but we'll do that later. Okay, so we've got the tail 2 and the head, which means that this, in counterclockwise order, this is going to be the number and this is going to be the tail. So this is highly inconvenient. We need to use a lot of wire crossing here to make this work. In fact, I think I almost lost sight of the fact that the result of all of that calculation is going to need to come into here. Well, the result of this calculation is a multiplication of 3 values. Oh, and one of those 3 values is the head, so I actually still need that. So I'm going to label this h so that I know that that's where the head is. And this is going to be a multiplication of the head with both of these numbers. Well, except that we can't just return the result of that because we want to return every result of every such multiplication across the entire sequence. So we need the result of this helper function to also be a sequence. And indeed, if you look at the existing calls here, we're just piping over to the next recursive call. So this is the only part where we actually need to decide what we return. We're going to add up all of those multiplications, aren't we? So we could do the adding up here. My original plan was to create a lazy sequence of the result of all of the multiplications and then just run the sum function on that. But we don't actually need to do that. We can just do the addition right here. So I want the c to be h times this number plus the recursive call, which takes both of the tails, which, by the way, I should probably label. Now, we know that the tail 1 and tail 2 are gonna go into the same recursive call as these here. This is the result of the multiplication of everything in the rest of the sequence. And I need to add that onto the multiplication of these. So why don't we just put the addition function right here? I suppose if I have the addition come out on the right here, then I can punch through this y and this y in order to get to here. I think I'm going to do that. We want to add the result of this with the multiplication of that, and h, which means that we need another copy of h. It would be more convenient if the h were further up. So I'm going to rejiggle this. And now I need to multiply the result of that with this one. Now, the result of that multiplication is going to go in here. So I think I'm going to put that multiplication function here. Fantastic. Okay, now let's quickly join up all of the remaining things. I think I can just put the declaration box right here. Okay, that leaves us with these zeros. Now that is a freaking humongous function. Okay, so now we've finished writing the double-circled one. We still need this one here. So this is going to be the one that is going to count how many times a value occurs at the start of a sequence. And it needs to return one more than that because we've already removed one element, right? So if there isn't like let's say the element we've removed is a 5 and there isn't a 5 at the start of the sequence, we need to return 1. So we need to keep that in mind. So let's start with this by declaring a box, by starting with a box declaration box. So this is going to be the sequence. Right, hang on. What is the order of operations? I think it was sequence first and then the number, right? I remember that this is h, the head, and it goes in here. And this here, bingo, that is the tail that is coming out of here. Because this is input, so that is output 1, output 2, and output 2 is the tail. So that means that in counterclockwise order, we have the sequence first and then the value. So we have a sequence and a value. And we need to remove the first element from the sequence in order to be able to tell what it is. But the sequence could be empty at this point. So we first need to check if it's empty. So in this case, if the sequence is empty, we need to return 1. And if the head of the sequence is different from v, then we also need to return a 1. Well, if the head is equal to v, then we need to count it. So we now need to make a recursive call, but the function needs to return two separate things. It needs to return the rest of the sequence as well. So let me make sure I get the order of those operations right as well. So here, this is an input, this is coming in. And then here, the number comes out first, and then the sequence which goes into here, into this recursive call. That means the first thing we output is the number, which means we've done this correctly. The second output wants to point to the right. If that sequence is empty, then the rest of the sequence is still an empty sequence. So this time we do want a 0. And then of course if h is equal to v, we do something. But if it's not, then we return the empty sequence again. No, wait, no we don't. No. We need to return the rest of the sequence right here, which is in fact seq, isn't it? We've looked at the head element and we've determined that it's not equal to v, so we need that head element to stay. So yes, it is the sequence that we want, not the tail. So far so good. Now, this recursive call is going to have two outputs. One of them is the value, and of course we need to increment that value. Similarly here, if h is equal to v, this one is just going to be the second output of this. So I'm going to put all of this right here, but because we need the h equals v twice, I'm going to move it over. Now what do we need to pass into the recursive call? Well, we need to pass in the tail, of course, because we've just processed one element, and then the value that we want to compare against stays the same. Now we need v in two places, so let's put the equal sign here right now. And since the equals function is guaranteed to return a boolean, I can make this an interrobang and this an interrobang. And we want h and v. This is the output to the function. I've made that same mistake before. This is the condition. This is where the sequence goes in. Okay, we want to call a lambda expression, so let's do that. I'm going to do that literally right here. So if this is the head, then this is going to be the tail, which means that this is the lambda expression, which is the sequence, and this is the input that it doesn't care about. Okay, now we need to free that t from these, because these seqs are going to connect up, obviously. But we also need the tail here. So why don't we punch through this line instead? And that leaves us with only the seqs, which we can easily just connect up. And then I'm going to move this up a bit. Okay, hopefully this is correct. So now we've finally written all of these helper functions. Now I just noticed that because I made this function here private, I should probably do that with the other functions as well. Not that it matters, not that I'm ever going to use that same function name, but, and in particular, the source file is not a library file, but either way, I'm still going to do this because it feels correct. There you go. Okay, so coming back to this, we've sorted the two lists, and now we need to pass both of those lists into this function. This is the double circled one, and then I'm going to write the rest of the code inside of this enclosed space. We expect the result of this to be a single number, right? Because we've done all of the multiplication and the addition. So all we need to do is turn that number into a string, and then we should be done. And then we can finally test this humongous piece of code, which I don't even know if it's correct. It's entirely possible that I made a mistake. And in fact, it's entirely possible that you guys noticed a mistake that I made. So, in which case, congratulations. Okay, so I'm just going to have that output point up. And because it's the main program, it doesn't matter. And now I'm going to run this. And I'm going to run it on the example first. Right, let's run it. Error, incorrect orientation of connectors. Bingo, I did make a mistake. Okay, let's investigate. We have this function here, and we're looking at line 6, character 46. So it's here. It's here. Why is... Oh, I see. Right, we want the output of this to point to the left. Because we have a single input, and we have two outputs, and we want those outputs to go left and right. All right, let's do that again. 511 is of course not the correct answer. We actually expected 31, didn't we? To see what's going on, let's try this with a simpler example. Let's start with a very simple example where we have just a 1 and a 1. What do we expect this to output? We expect this to output 1 because we're multiplying the number 1 with the number of occurrences, which is 1 on both sides. So we should get a 1 if I do this. And we get a 49, bingo, 49 is the ASCII value or the Unicode value of the digit 1. So there is at least one place where we forgot to turn the string into an integer. When I split this up into the two strings, I should just do the conversion right here. So we need to insert here and here, because here we are obtaining the head of the strings that we got from standard input, which means that that is the first input, and the second input is, of course, the separator, the 3 spaces. Okay, so we want to convert that from strings to integers. So now let's run that again, and we are getting a 1. So if I put a 1 and a 2, I expect 0, right? Because now they have nothing in common. And indeed, I get a 0. So let's try the original example again, and we expected 31, and indeed we get 31. So I think this is working. So now comes the big moment, right? I want to put in the original text, and I want to measure how long this is going to take to see if this was even worth it. The previous implementation that we had took 28 minutes and 13 seconds. Let's see how long this one is going to take. I fully expect it to take at least, I don't know, 10, 15 seconds, but possibly even a minute. I mean, it is... Whoa! Oh, whoa, it's 7.7 seconds only. That was a lot faster than I expected. And the result is exactly right. We did it. We brought it down from 28 minutes to 7.7 seconds. Wow! Now all that's left for me to do is to lay this out in a way that I'm happy with. You know, I'm just going to put some of these side by side. Maybe a bit further up, maybe a bit further right. Okay, like that. So that it lines up beautifully down here. And then maybe this, the main program can go over here. And then we can remove all of this space and all of this empty space at the bottom. So we're done with the first day of Advent of Code 2024. This is our solution to the first challenge, which consists of a single program which uses only library functions, although we did write the sort function for this and we added it to the library. And then, of course, the second day we have this monstrosity of a program here which uses 3 helper functions, and the only mistake I made while writing this was to forget to turn the integers into strings. All of this complexity here, first try. So what do you think? Did you solve Advent of Code 2024 as well? Did you maybe come up with a better solution? Did you maybe do it in Funciton as well? Probably not. But either way, I'm hopeful that I'm going to continue with the rest of Advent of Code 2024. So hopefully I'll see you for day 2 in the next video.